We are very lucky that Albert is here. It was quite a luck that we put characterizations workshop, and Albert is here because Albert is the world expert in Cathodoluminescence spectroscopy. Also a world expert in different photonic materials, so we are very lucky. He's here for 3 months?
3 months, yes.
3 months as part of Fellowship. I hope that I said that correctly.
Yep.
So, like I said, tomorrow we will have a bit of talks on other aspects of his work, but from the part of characterization, CL is very interesting techniques. We don't use it so often here at UNSW. We just start some kind of collaboration with Albert on CZTS, the genus, and before that, but we as the characterization group also try to see how we can use CL for silicon wafers, so that will be an interesting topic. But it will be great for all of you to understand how CL work and what you can get that, so maybe for the organic group as well, and the perovskite definitely. So please welcome Albert, and it will be great.
Thanks, Steve, for your introduction. So, I'd like to talk about cathodoluminescence microscopy, and I just assume that nobody knows about this, okay? I'm going to really start from the basics. It's a measurement technique for doing optical measurements that uses electron microscopy. And I think it can have some really interesting applications in photovoltaics, as Ziv said. There may be, things you can do with cathodoluminescence that has not been done before. And one of the reasons I'm here at this workshop here, but also visiting the lab here, is to see if we can set up some collaborations using this technique to in the end make better solar cells. So I'm from the Center for Nanophotonics. It's a national research lab in Amsterdam in the Netherlands. And so let me start with a very simple question. If I have a very small object, this is a microscopy, electron microscopy image of a metal nanorod, but it could be, this could be a doped region in a semiconductor solar cell or a small contact area, just something small, right? 250 nanometer. That's much smaller than the wavelength of light, as you know, which is 500, 600, 700 nanometer. So if we want to see something inside or the optical properties of this structure, and we use just a normal optical microscope, we won't see anything, right? So the diffraction limit tells us it's down to 300 nanometers, sort of the features we can see. So then in optics, there was a whole research field called nanophotonics, where people develop new instruments and see, okay, can we somehow squeeze the light to a smaller scale and do measurements at the scale below the diffraction limit? And one technique is called near-field microscopy. You see an image on the right there. This is a needle with a very small silicon core here, covered by a metal outside cladding. And this gap here could be 100 nanometer or so, sometimes even a little bit smaller. So you can imagine if you scan this over the surface, you can pick up light that propagates or is localized at the surface. You can make some optical images. But still, it's very hard to do this at a resolution smaller than, say, 100 nanometer. And there are lots of problems. You can imagine these tips are hard to make and they will break, and the tip actually affects the measurement. So it's a very interesting technique, for sure, but also has its limitations, certainly in spatial resolution. So then let's go one step smaller and say, what is a very small spot that we can take using an characterization tool? It's a spot of an electron beam. If you do electron microscopy, scanning electron microscopy, make a cross section of a solar cell or make a top image in SEM, you scan an electron beam, and the spot size of the electron beam is a nanometer or so typically. So it seems like that is the ideal tool for optical characterization, right? Because you just have a spot that's a nanometer, and you can scan it and you can place it anywhere, so you just use it, electron beam, for imaging. But then wait, we were talking about optical imaging, right? And an electron image in an SEM, what that is the electron beam scans, and then the secondary electrons that are created by this primary electron are detected, and they form the image, right? No optics. And what I'm going to show you now in this talk is that actually electron beam can also make optics, can make light come out. And that's called cathodoluminescence. So the electron beam will scan over the surface, and at every pixel, at every position where the electron beam is, we're now going to study what is the light that is emitted. And this, in fact, is a very old technique because geologists have been using this for 40, 50 years. So if you're a geologist in the field and you pick a piece of mineral and you want to know what it is, you can stick it in an electron microscope, you hit it with high energy electrons, and then the radiation, the light that comes out, the cathodoluminescence, it will tell you what the mineral is. Is it calcite? Is it granite? You see here 2 pictures, that I took from Wikipedia. There's just so many examples of this. These are optical images made in an electron microscope, right? I don't know exactly what the colors are here. They could be a representation of the wavelength of light that's emitted or the intensity of light. There's many ways to make these CL images. And also, for our purpose today of nano characterization, these images are not the right examples because look at the scale bar here. This is 100 microns, so this is the typical grain size in sandstone. But it tells you, you put something in the electron microscope and light comes out, and you can make a map, basically, because at every pixel you plot the intensity. So what is then the fundamental mechanism behind this? And we should distinguish 2 ways the electron beam can generate light, the incoherent and the coherent way. So the incoherent one is in a way the easy one, in a certain way. So that's what we just saw with the geologists. Because what happens if you have your chunk of mineral, electron beam comes in, it penetrates, and it slows down, it goes a micron deep into the crystal that you analyze. And there it releases its energy to whatever emits light. It could be defect centers, but this could also be a semiconductor, it could be quantum dots, anything with an optical transition can be excited by an electron beam. The excitation mechanism, it can be lots of different ones. There's impact excitation, where a high energy electron can generate excitation of, say, a rare earth ion. You can make electron hole pairs that diffuse through the material and then in the end excite a quantum well or a quantum dot. In any case, what is important, there are many steps between the electron coming in, then all these secondary processes, non-radiative recombination, excitons, electron hole pairs, and then finally the light comes out. And that means there is no phase relation, there is no relation between the moment that the electron comes in and that the photon is emitted. And this is why we call this incoherent luminescence. In the cartoon on the left-hand side, you see the electron beam comes in, it generates whatever emits light here, and typically that would then isotropically emit light inside the material. And then the way the light is emitted from the material is indicated by this curve. This is the intensity as a function of angle. So if it's isotropic inside, then just from the Fresnel equations for reflection and transmission, you get this cosine distribution. It's called Lambertian distribution of the light that's emitted. So most is going out, and the further you go away, the less the intensity. So that will happen with any bulk material that you hit with an electron beam that can radiate light, a semiconductor, a diamond NV center if you're interested in quantum optics, erbium doped glass if you're interested in telecommunications and so on. Then the other mode is called coherent radiation. And this is very interesting from a very fundamental physics point of view, because what really happens here is very simple. So if I have an interface between a vacuum and a dielectric, I have a piece of glass, say, or a silicon wafer, and here comes my electron, then my electron is a point charge, it's a negative charge. That means it will make an image charge. So now I have a minus and I have a plus, I have a dipole moment, right? It's a very special dipole moment because as the electron moves towards the surface, the dipole starts to move, and then if the electron enters the substrate, dipole's gone. Okay. So, but dipoles we know, because everything, in optics is about dipoles that radiate, right? The quantum dot is a dipole moment that's radiating. A fluorescent dye is a molecular transition. It's a dipole. It radiates. So also this dipole artificially made by this electron will want to radiate. And it will radiate to whatever it can radiate to. And you can say it is Fermi's golden rule that tells how the radiation is released. Fermi's golden rule says if I have optical excitation somewhere, then the excitation will be released to whatever the possibilities, the modes are. A mode is a solution of the Maxwell's equations, or where can the light go? And the simplest one is indicated in red here. If I just have a point dipole standing on top of a dielectric interface and it likes to radiate, it will create these lobes, these dipolar lobes. And that's what you see here. And this radiation is called transition radiation. So every time an electron passes through an interface of 2 materials with 2 different dielectric constants, you get this transition radiation. But now, since this is light is created by this dipole, there is a phase relation between the moment that the electron hits the sample and the moment that the photon or the optical wave is released. And that's why we call this coherent radiation. Now for the applications in PV, I think the incoherent is the most interesting one. And so what I'm going to do is show you a few very simple examples of the coherent one and then really move to incoherent, because I think we can use it in PV, as I said. Let's look at the technology first. How does this work? So schematically, this is an electron microscope. This is the electron column. So here's a source, 30 keV electrons are accelerated, and here's the chamber. There's your sample holder inside. And so what is put inside between the electron column and the sample, it is about 1 centimeter space. There's this parabolic mirror, and there's a little hole in there. And so the electron beam goes through the hole, hits the sample. Oops. Light is emitted, goes to the parabolic mirror, and then it's with the lens guided outside to this black box here, and the black box has all the optics that can spectrally analyze the light. So at every pixel, on every position, we make an electron microscopy image, but also an optical image. And a second mode is the following here. Then the light is emitted at a certain angle from the sample, and now that is projected onto a CCD camera, where now every pixel on the camera is uniquely linked to one particular angle of emission. So basically you print the angular distribution on a CCD camera. This is interesting if you're interested in, say, photonic crystals, because angle means wave vector, and we call this therefore momentum spectroscopy, because the image on the CCD camera is basically a Fourier image for the specialists. It tells you what the band structure of material is. So this is an instrument we've developed in our lab. As I said, the geologists do this already for 40, 50 years, but they didn't have the spatial resolution, didn't have the sample holders to align the electron beam, and they also, in the commercial CL systems, really didn't have the right optics to do this in a right and in a normalized, and in an efficient way. So we decided to engineer that ourselves, and that's what is all in this black box. And then realized there could be a commercial market for this. So we started a company. The name is Delmic. And this actually is the commercial product that is now on the market. Many of them have been actually sold worldwide. That is now the new version of this black box. It's very interesting to see. If engineers turn your lab equipment into a commercial product, it's completely redesigned, right? Of course, this optical box just has an optical rail and lenses and mirrors. This is how we, build optical setups. But if you want to make a product that can be replicated and it can be, maintained and is reliable, you have to re-engineer the whole thing, and they did a fantastic job in doing that. Here's the parabolic mirror. Here's the little hole you see inside. Actually, I have a better image here. This is a self-portrait of the electron microscope. I'll spare you the details how this is taken, but this is the inside. This is the parabolic mirror here. This is a little hole where the electron goes through and it collects the light. Okay, so what can we do with that? In sort of nanophotonics research, so understanding how light behaves at the nanoscale, there are two elementary particles. There are metallic particles that have plasmon resonances, and there are dielectric particles that have what is called Me resonances, dielectric resonances. A resonance means the light is confined in the particle, it's strongly confined, and it can then scatter out again. And so we would like to understand and measure these optical properties at the nanoscale, and we had no tools to do so. This is why we developed this instrument. So here's one example. It's a gold nanoparticle. It's only 50 nanometer in diameter. And if we park the electron beam on top of the particle, this is the light spectrum that's emitted. So here you see a first example of a cathodoluminescent spectrum of something that in itself is completely inert, right? We're not looking at fluorescence of the gold, or there's no dopants inside. This is a completely inert dielectric or metal. And the radiation is induced because this electron beam comes by. It pulls on the electric charges in this metal nanoparticle that then start to radiate, and that the radiation that you see here is the spectrum. And this is the plasmon spectrum, the resonant plasmonic spectrum of a gold nanoparticle. Is this efficient? Well, the count rate is 10 to the minus 4 photons per electron that comes in. So you may say, that's very inefficient. But then, okay, that's still a bit arbitrary units, right? You have to put in the electron current, and if you multiply the two, it's 10 to the 7 photons per second coming out. Okay, and we have very sensitive detectors that basically count every photon. So actually we are overwhelmed by photons. So to take this spectrum, it maybe takes 60 seconds or so. Now the nice thing about CL is we can scan the electron beam, and that's what you see here. This is a map of this radiation at the peak wavelength here at 575. We just scan over the particle, and you see if we are on the particle, it's most intense. That's what this bright color says here. And you can see we have to basically reproduce here the contour of the particle that you see in electron microscopy. So scale bar 50 nanometers. So this is an optical image. And here you already see we have beaten the optical diffraction limit by easily a factor 10. You can also say, well, then if it's all so sensitive, what happens if we park the electron beam not in the center of the particle, but we park it on the edge? And this is just as an illustration, but this is the angular profile. Remember we had the CCD camera, so by imaging on the CCD camera we can tell is the light directed in one direction or in the other direction. Well, if we park the electron beam on the right hand side here, if the particle is here, we park an electron here, the particle beams radiation to that direction. And of course if we would park the beam on the other side, the light's coming out in another direction. And there's no time to go into all the details, but I want to tell you here is that metal nanoparticles have many modes. They have many ways in which electromagnetic energy can be stored. They can be dipolar modes, dipoles stand up, dipoles can be in the plane, they can be quadruple modes. Again, too much detail, but I just want to say that, there are many resonances in these particles, and they all interfere, and the interference causes that light is going out in one particular direction. And what I like about this experiment is it shows the coherence. The fact that an electron comes in, excites all these charge distributions inside, and they coherently interact. They all have a phase relation with the electron, and then light comes out. So, can we understand then a little bit more in detail that coherence, or that electron, as it comes by? What were we saying? So we had this interface, electron beam comes by, and really we have to look at the electric field of the electron. So if you're an observer here, and here comes an electron, what do you observe? So first the electron comes nearby, it means the electric field is standing up. And as it comes by and it goes down, of course the electric field turns sign and goes down. Right? There's also a radial electric field. If the electron is far away, then you don't measure anything here. If the electron beam comes closer, that electric field goes up and then it goes down again. Right? So that's what you see plotted here. It's the radial and the parallel electric field components as an electron moves by. And look at the time scale here. In 5 femtoseconds, it's all over. Right? So there is just a little wiggle of electric field in space in 5 femtoseconds, and then it's gone. Right? So that's interesting, because now it makes you realize an electron is really like a light source. It's just light is also, oscillating electric field, right? It's nothing else, right? But this electron is doing exactly the same. It's an oscillating electric field, except it's only one oscillation. Okay, so what is a 30 keV electron? It's a 1 femtosecond or a 5 femtosecond light source, right? It's only 1 nanometer in diameter, right? And if I take the Fourier transform, if I want to convert this from the time domain to the frequency or the energy domain, the effective bandwidth, the energy spectrum of this oscillation goes up to 40 electron volt. Okay, so we have a light source that is 5 femtoseconds long. It's 1 nanometer big, and its energy spectrum goes from 0 to 40 eV. It's a white light source, basically. So I would claim really electron beam is the ultimate light source. Right? And really in our lab, we less and less use lasers to do spectroscopy, because we make samples in the clean room. Then they have to go in the SEM. We have to check if the lithography worked out well. And then, well, you might as well just do the optical experiment in the SEM as well. So just to summarize that, what is the difference between a laser and an electron beam? If you have a continuous wave laser, the electric field just oscillates in time and has one frequency, right? So the frequency is very well defined. I have a helium-neon laser at one wavelength. And the diffraction limit is half the wavelength, 250 nanometer. If I have an electron, on the other hand, I have one wiggle of the electromagnetic field, and that corresponds to a very broad spatial frequency, energy bandwidth, and so I have a white light source, basically. Okay. Now, okay. So what's the resolution then? What is the? Okay, we say the spot size is a nanometer. Okay, so are we now saying we can do optical microscopy at 1 nanometer resolution? Well, now we have to be careful, because what did we mean with 1 nanometer? That means if I have an electron in an SEM and it hits the surface, the charge distribution of that electron is about 1 nanometer big, right? or there's some wiggle, the source, and there's some optics of the electron beam. So altogether the focusing, I can focus an electron beam to 1 nanometer, right, in an SEM. But really, we were talking about the electric field, right, that was inducing all these optical transitions. So how big is the electric field? Well, it turns out, if the electron beam is moving, the electric field is sticking out. It's called an evanescent field, it's decaying. And that decay is plotted here. So here's electric field or magnetic field, we can plot both, and here's the distance. This is in reduced units. It means I can make this plot for any energy or velocity of the electron, and I know the Lorentz contraction factor, and this is for a given frequency. I want to excite something, say at 800 nanometer. Well, then this is the field distribution of the electric field about the electron trajectory. Okay. So here's the corresponding distance scale on top. So you can see this falls off at 10 nanometer or so. So the effective resolution of a measurement resolution, at which the electric field falls off, is about 10 nanometer. Okay. Now let's use that to our advantage in the design of photovoltaic materials and systems. Here is an example of a metal nanowire grid that we developed on a silicon heterojunction solar cell, where there's always ITO at the surface, and we don't like ITO because it's brittle, it's expensive, it's indium, it's a rare element. So many reasons you want to get rid of ITO. And so one way to do that is get rid of it and then replace it by a metal grid that you see here. And this is the SEM image. So this is a gold nanowire grid. It could be silver actually also. In fact, I'm wondering if it's not silver. No, it's okay, it must be gold. If we do this right, then the effective conductivity is the same as ITO, but the wires are so small that the light doesn't see them, right? Formally, you have to say the light excites a plasmon and the plasmon scatters inside the solar cell. Okay, but anyway, the structures are so small that the light will just go straight through. And then on the right-hand side, this is the CL image. So to the first sight, it doesn't, look very, just looks the same, right? So what does it mean? We have scanned the electron beam. And rather than on the left side take the secondary electron image, SEM, take the light image that comes out. But so you have to realize this picture is an optical image. It's the light emitted at 700 nanometer. Okay. But look at the length scale. So this is a micron. These wires are 60 nanometer wide, right? So, or 90 nanometer wide. And they emit light because they're plasmons that, radiate into our detector. So this already tells you how high the spatial resolution is. You can make an optical map of the wires. And so this is how we did CL in the end. This is the paper that we published that showed we can make transparent contacts and make very good silicon hit cells with this. You can wonder, okay, let's look at this look at this width of these wires in a little more detail. These are line scans. So in the SEM image, I can plot the intensity of the brightness, so the sort of the brightness of the wire here. That's the blue graph here. And I can do the same for the CL. And so the CL signal is a little wider than the SEM, so this proves that indeed this electric field is sticking out and the beam has a certain width that widens the measurement. Interestingly, if I go to a higher energy, if I take 20 keV electrons, I get a wider image than if I go to 10 keV. That's because at higher energy, this electric field sticks out more, right? So the resolution is actually not as good at 20 keV than as at 10 keV. So it's very peculiar. This is a measurement technique where if you raise the energy, the resolution actually gets worse. Now, does this only work for metallic structures? No. This works for anything that has a resonant, has some optical modes. So we can just replace the gold or the silver by silicon and look at the silicon disk, you see it here. And then we park the electron beam on there, and this is the radiation that comes out. So again, this is a completely inert semiconductor. There's no quantum dots, there's no band gap emission here. It's just a dielectric. But because of its peculiar shape, it can store light, and it can do that only at one frequency determined by the diameter. And that's what you see here. And this is called the Mie resonance. So if the particle is small, 80 nanometer, this is the optical image of the nanodisk. Then it has a resonance in the UV. And if I make it bigger, if this is about 400 nanometer diameter, then all these peaks appear. These are all the higher order resonances of light that is confined inside these particles. And so for all these resonances is all new to you. Just the analogy with acoustics is all you need. Just you have a drum and you have in lowest order frequency, you have higher order modes, you have higher order resonances. In optics, it works exactly the same, and sometimes the equations are also the same, not always. Okay, and this is my last image of this sort of coherent emission. This is a photonic crystal. For those of you who've heard about this, this is a silicon nitride membrane with holes punched in it. And then there's a cavity inside, that's the yellow region here. This is where light can be stored. And this is an image taken by scanning the electron beam and detecting the emission at one wavelength, at 690 nanometer. It's the cavity resonance. And this is basically a map of the light inside the cavity. Right? So this is, you can see our optical microscope, our electron microscope, provides an image of how light is confined and stored inside this cavity. And look at the length scale again, 300 nanometer. If you see how sharp all these features are, you can really probe light at extremely high spatial resolution. So that was about the coherent radiation, where the light, and it's this dipole model. The dipole creates modes, the modes radiate, and the modes can be plasmons or Mi resonances or photonic crystal cavity modes. Now let's go to the incoherent process, where in a way, most cases we don't know exactly how the excitation works. We only know a high energy electron comes in and light comes out, and everything in between is incredibly complex, right? It's complex because everything I showed you so far was solving Maxwell's equations, and that we nearly always know how to do. Now, in the incoherent radiation, you have to solve Schrödinger's equations because it deals with electrons and electron holes and potentials and band structure. Can't be done, right? There's only a few, you can, in very simple systems, we know how to calculate band structure, but to calculate how CL is generated and how efficient is impossible. But it's okay, we can use it as a tool. And here's an example. We take gallium nitride from the blue LEDs, and then we make indium gallium nitride. Well, not we have collaborators in Germany that are really good at growing these quantum wells of indium gallium nitride. And then we come in with 30 keV electrons. And this is a simulation, it's a Monte Carlo simulation. So you randomly shoot electrons and just calculate how they are scattered. You see they form a whole cloud of electrons. And then this is the light that comes out. So you get radiation from the indium gallium nitride, that's this peak here at 450, and you get radiation from the gallium nitride substrate, it's called the yellow band. And now, for example, what we can do, this is taken at I think 10 keV. We can vary the electron energy and see what happens. So if we take a very low energy at 6 keV, in fact I think that's this simulation, 6 keV, we only get the luminescence, the cathode luminescence from the gallium nitride. But as we increase the electron energy to 30 keV, so that means the electrons penetrate, so they come from the top, electrons penetrate deep into the substrate, we also get the cathode luminescence from the substrate, and that's this yellow band of gallium nitride. So this already tells you, if you vary the electron energy, you become sensitive to either the surface, if you take low energy electrons, or if you want to look in the depth, you increase the energy of the electrons. This is a project we've done in the past year on a sample made in Gina's group, where so it's a CZTS sample on molybdenum with a small cadmium sulfide buffer layer at the surface, where we have a cross section here, and then we have also a top view, and I see a very grained top view structure. And then again we do CL at 5 keV. So here's the cross section again. This is the CZTS, here's the molybdenum film. No, this is the molybdenum, here's the glass. No, I'm wrong. This is the molybdenum, and down here is the glass. So at 5 keV, we mostly hit the Cad sulfide near the surface and a little bit of the CZTS. 10 keV hits the CZTS mostly, and 30 keV also, but it also goes into the molybdenum. And you see a distinct difference in the spectrum. If it's at 5 keV, we see this band here at 750, and then at the high energies, we see this band at 900. So the 900 band is clearly from the CZTS, and what we see here must have to do with something that's very close to the surface. So then, you can make a spatial map. You can look at the surface here. There's this grain structures here, and you want to know each of these individual grains. What are they? What material are they? Well, then you put the electron beam on this position. You take the spectrum, that's the yellow spectrum, or you put the electron beam somewhere else, and that's the other spectrum. So here you can see, you can position the beam, and you can locally measure what the spectrum is. And this little particle we found was probably cadmium sulfide rich. Here's another example. This is not done by our group. This is from the Delmic, our startup company. Worked with a group in Helmholtz Center in Berlin that are very good at making CIGS solar cells. And this is a cross section that they made. So it's a zinc oxide top layer, then there's a heterojunction between cat sulfide and CIGS and molybdenum back contact. 1 micron scale. This is a cross section. And so what you can do in the cross section, you can scan the electron beam through the cross section. Right? So you make a scan, basically you start at the surface and then you scan, so the electron beam is now normal to the cross section. You scan down and you measure the band gap. And you know in CIGS cells there's this band gap grading to get rid of recombination at the molybdenum back contact as much as possible. And that's measured here. Here's the band gap energy near the surface, and then band gap goes from 1.2 eV to 1.3 eV. So every data point here is a CL spectrum where at every depth you plot the band gap of this structure. And then finally, I want to show you these nanowires. Here is a side view, a gallium nitride nanowire grown by MBE with indium gallium nitride quantum wells in between. And if you look at the top, these are these hexagonally shaped wires. And then you park the electron beam on each individual wire. So for every wire you can take a spectrum. You see they're completely different in this case. And this is a map of basically the color tells you the wavelength in this case. So this nanowire in the center emits mostly green light, the other one more on the blue side. Here's a more precise intensity distribution. So look at the scale bar, 200 nanometers. So you can really reveal very special features in the luminescence intensity that are linked to these facets on the nanowires. And this is important information for the people that grow these wires. And then as a last thing, really for the specialists who are interested in this, is photon bunching. So if you take a quantum well and you irradiate it with electrons, then many photons come out. And you can build an interferometer, a Hambry, Brown and Twiss interferometer. That's the thing shown up here, the structure shown here, where light comes out and it goes to a photodetector that gives a click. And then you wait till the second photon comes and it goes to another photodetector that also gives a click. And then you measure the time between the two clicks. And then you build a histogram. So you just repeat this experiment many, many times. And then the histogram is called the photon correlation function. Tells you what is the fraction of photons that appear after each other within a certain time interval. And what you see is at time 0, there's a strong peak here. It means that most photons, or I should say a very large fraction of the photons, actually come out at the same time. And this is called bunching. And the model behind this is that an electron comes in, and one electron creates many photons, but they all come out at the same time, right? And that's why they have strong bunching. And bunching or anti-bunching is a very important feature in quantum communications. If you have a single photon emitter, for example, you don't have bunching, you have anti-bunching, because a single emitter can never give two photons at the same time. So the peak here would go, the peak would become a dip at 0 time delay. So with that, I think this is my last slide. I want to end with a new variation on our CL microscope that we're building right now, and that is to build in time resolution. So far we've scanned the beam and we've measured the spectrum at every position, but wouldn't it be nice if we could measure the lifetime at every position, right? Because it can tell us about, it's the fluorescence lifetime, it can tell us about carrier lifetime, carrier recombination and so on. So what we do is in the electron microscope we put a beam blanker, 2 electrostatic plates, and if the electron go through, we put a 50 megahertz electric field and then a small aperture down here, and that way we pulse the beam on the sample. And actually just yesterday we've seen we can make pulses as small as 30 picoseconds on the sample. And if you want to go even lower, then this is what we've also just installed. You drive the cathode with a laser pulse. So normally the cathode is heated, it goes to a high extraction voltage, you extract electrons. So now what you do is you lower the temperature, you lower the voltage, and then you zap the cathode with a 200 femtosecond laser pulse. And then by photoemission you create electron bunches that then are accelerated. And then you can make 1 picosecond electron pulses. So that's the future, but this will enable us to make lifetime maps at extremely high spatial resolution. And that's where I want to end. Thanks very much.
Thank you so much, Albert. Questions?
Thank you. That's remarkable what you can do with an electron microscope and a spectrometer. I wondered if you could elaborate a little bit on the coherent mechanism, because I mean, you gave us this very clear picture of you have the electron approaching the surface, and which is then the dipole. What I immediately thought was, okay, this could be very broadband, and I think that was what you were saying. But then you went and showed us plasmon emission, where I guess that's the only mode that couples efficiently into free space. But when I just have a planar surface, am I really getting white light off that planar surface?
You are. I don't have the spectrum here, but indeed, if you just take a silicon wafer, over the visible spectrum, it's completely flat. If you take a gallium arsenide wafer, then of course you get the band edge luminescence plus this transition radiation, so I get a completely flat spectrum plus the band edge.
So you could generate sort of UV and anything up to the photon energy.
Of course, in the end, then you have to deal with this small efficiency here. You can think about lithography. If you want to do XUV lithography, you want to make XUV light. This is a way to do it, but then it turns out for that application, the intensity is quite small.
Any limitation of the energy beam, and because of that you don't use organic, or?
Good question. So, yeah, organics, as always in SEM, they can degrade, right? And so then you go to lower energy, maybe 5 keV, and we have done CL on pentacene and tetracene organic materials. Some on perovskites also, but they also degrade under the beam. So that's well. So there is a dilemma, and yeah.
So let's thank Albert again for a great talk.
Thanks.